Hello, I would like to welcome you to lecture 6 of 3N03. We'll be starting today on our semiconductor part. We finished already the circuit review part. So we'll now start to talk about the basic information we need to start discussing diodes and PN junctions. And the material covered in this lecture is from chapter 1 of the textbook, pages 1 to 16. We already covered part of that in an earlier lecture, but the total material we covered so far will be covering this lecture and previous lectures from pages 1 to 16 of the textbook. Okay, we discussed before the Bohr model for atoms, and we agreed that an atom usually consists of a nucleus where you have protons, which are positive charges, neutrons, which are neutral charges, and they are simply surrounded by electrons orbiting around this nucleus in different orbits or different shells. We agreed that the number of electrons is equal to the number of atoms, a number of protons is equal to the number of neutrons is called the atomic number. As we agreed that these electrons orbit around the nucleus in different shells, and each one of these electrons has its own energy. The closer electrons are to the inside to the nucleus, the less energy they have, and the farther outside, the more energy they have. And the further they become away from the center or from the nucleus, the more likely they are able to break free from the atom and become free electrons. One thing I should mention, even though in most books they draw the nucleus to have a comparison size like the whole of the atom, the truth is that the nucleus is like a golf ball, a very tiny ball in a soccer field. So most of the volume of the atom is actually empty. Most of the volume is actually empty, and the electrons keep on circulating around the nucleus in their own shells. So for every shell, the Bohr theorem states that for the nth shell, the number of electrons that can exist is 2n squared. So for the first shell, which is the innermost one, you can get two electrons. For the second shell, where n is equal to 2, you get 8 electrons, and so on. The electrons in the outermost shell is called the valence electrons, and this shell is called the valence shell. And these electrons are the ones that have the highest energy, and they are the ones that are least bound to the nucleus, and they have good chance of breaking from the atom if they are given enough thermal energy. And sometimes some of the atoms, this can happen even at room temperature. So, and when that happens, one of these electrons will break free from the atom, and then it becomes a free electron. And when it breaks free from the atom, it leaves behind a positive ion, because for the whole atom now, the positive charge exceeds the negative charge, and then the atom is not neutral anymore, and then you have a positive ion left. This naturally leads to the classification of materials into conductors, semiconductors, and insulators. In the case of conductors, and then here I'm showing you the copper atom, there is only one electron in the outermost shell. So while the core of the atom has the rest of the nucleus and the rest of the electrons. So the effective charge, the electropositive charge seen by this single electron, is really the charge of one positive proton, because as I said, the number of electrons is equal to the number of protons, so they are all equal to 29. But if you take only the core, which excludes the outermost shell, you will see that you have here the net charge is that of only one proton. So this electron is really not tightly bound to the atom, and then it can break free at room temperature. And most conductors are single element material, like copper, like aluminum, like iron, and so on. They have usually large number of free electrons for conduction. These electrons in the outermost shell, they are not really tightly bound to the nucleus, and they can break free at room temperature, allowing large current to flow if an electric field is applied. The second type of material is called semiconductor material, as in the case of the silicon atom. The silicon atom will have 4 electrons in the outermost shell, and it has 14 protons. So the core which contains all the nucleus and the electrons except the outermost shell, the valence shell, will have a charge of 4 protons. So somehow these electrons are bound to the atom, but not in a strong way. And if they are given enough energy, they can break from this atom. At least one of them can break and then becomes a free electron. So their conductivity is definitely less than that of the conductors. And most of these semiconductors, they can be single element like silicon, they can be compound like calcium arsenide and so on. There are so many of these semiconductors, but they can be either single elements or compounds. The last one is the type of insulators. And the insulators, the valence electrons are really tightly connected to the atom. They cannot break free from the atom. And even if there is a very strong electric field applied to them, electric field, as I explained earlier, will try to force electrons to drift against its direction. And it will try to make positive charges to drift in its direction. But this cannot happen in the case of insulators, and this is why we use them for insulation in wires and cables and so on. Another way of looking at different types of material is through the band energy gap or energy band diagram. Energy band diagram simply describes the energy of the possible electrons and charges that we have. For example, let's take a look at conductors. We have the electrons in the valence band who are in the outermost shell can assume certain values for the energy. So these are the energies here that can be assumed for electrons in the valence band. But for electrons in the conduction band, these are the free electrons. You can see these are their possible energies, and you can see there is an overlap. This is simply saying that electrons in the valence band, who are the valence electrons, have enough energy themselves to break from the atom and then become conduction electrons, to become free electrons. So this is one way of looking at it. Zero energy gap. Electrons really do not require much energy to break free from their atoms. And the transition from the valence band to the conduction band is very easy transition. For semiconductors, somehow situation is a little bit different, because the electrons in the valence band have this certain set of values for their energies. While electrons in the conduction band, they have to gain enough energy to become free electrons. They have to cross what we call the energy gap. So little energy would not be enough to make them break free. They must assume at least minimum value of energy to break free. And this minimum value of energy is called the energy gap. And when they gain this energy, these valence electrons become conduction electrons, and then they move to the band gap. Energy band gap means, or conduction energy means, they have enough energy to become conduction electrons. So this is a moderate energy gap. They have to gain some energy, not big energy, but some energy. And there is a possible transition. There is a possibility that electron will break from the valence band, gets enough energy, make the jump to the conduction band, and then becomes a free electron. For insulators, the situation is on the extreme side, because the difference between the valence band and the conduction band is big. Electrons will have to gain large energy in order to make this transition, and when this happens, usually means that the material is breaking. We reach the breakdown of the material, but without material breaking down, this is an impossible transition. In other words, the electrons in the valence shells are tightly connected to their atoms. Even if you give them enough energy, sufficient energy, they will not be able to cross this gap. They are still attached to the electrons. The only way to make them cross this gap is to really make the material break down, to make the material collapse, and in that case you can have such a transition. And this is what happens when we get a fire in a house due to a break of the insulation. But this is not how we use this type of material. In regular condition, this is an impossible transitions, and this is why we use these materials as insulators. We talked in a previous lecture about covalent bonds. We agreed that in many materials, atoms will share some of their outermost electrons to create some state of chemical stability. And here this is shown for the case of silicon. You have one silicon atom. It has 4 electrons in its outermost shell, only 4, but it shares 1 electron with a neighboring silicon atom to create what we call here a covalent bond. This is a covalent bond. Each one of these 2 atoms will contribute 1 electron to create a covalent bond. And this will create the chemical stability of this structure. So you can see the outermost shell now for the silicon atom will be complete by sharing 1 electron with a neighboring silicon atom. And it does this with 4 other silicon atoms to get 8 electrons in the outermost shell. And another way of drawing it is this way, where you show every 2 atoms is contributing 1 electron. Every atom is contributing 1 electron to the covalent bond, and every silicon atom is creating 4 covalent bonds with 4 neighboring silicon atoms. So this is another diagram that shows a silicon crystal, or the structure of a silicon crystal, or the intrinsic structure of a silicon crystal, where covalent bonds are done or are created between one silicon atom and its neighbors in order to guarantee the chemical stability. As mentioned earlier, conduction can happen in semiconductors, but we have to give the electron enough energy. So here we have one silicon atom. It's creating a covalent bond with another silicon atom. But if you apply enough heat, or even some other means, maybe through light, we can give this electron, the electron that was here, enough energy. This electron will be able to cross the band gap, the energy band gap, and then become a free electron. So what it does, it moves from being a valence electron whose energy is in the valence band, and then it crosses the energy gap to become a free electron, so it can move freely now in the material. When it does so, it leaves behind, you can see, an empty space in the bond. We call this empty space a hole. We call it a hole. And because the structure is electrically neutral, this hole effectively has a positive charge because the electron left its place, so this hole effectively has a positive charge. And this is how we think about the process of generation. A process of generation means that if you give the electron in one of the bonds enough energy, it will break from its bond, it becomes a free electron. It will leave behind in the valence band a hole, a positive hole. And at thermal energy, at room temperature, is sometimes sufficient for this process to take place. So this is how it happens physically, and this is the explanation of this process of generation of electron-hole pair in terms of the energy band gap. Electron gains enough energy to cross the band gap. It becomes a free electron, so its energy is within this range, and now free electron can move throughout the material if there is enough, if there is electric field applied or so on. It leaves behind in the valence band a positive hole. So this is called the process of generation of electron-hole pairs. And you will hear the word generation very often in the study of semiconductors, generation of electron-hole pairs. The opposite process to the process of generation is the process of recombination. So you have here a free electron that will simply jump to fill a hole in the covalent bond, so making this covalent bond complete again. And then it loses its energy in the form of photon emission. So it radiates energy. Really, a photon is really what creates light. It releases its energy in the form of light. And this can happen according to frequency or color that depends on the energy it lost. So here they have another electron joining a hole. So this is called the process of recombination. Another free electron joining a hole. So these two will cancel out. The electron will lose its energy, giving rise to a photon, and so on. And a photon is what constitute lights. So light is really photons, is really packets of energy or quantas of energy. Okay, in semiconductors there are two types of currents we are going to be seeing. We talk about them. One of them is called conduction band current, the other one is called valence band current. In the conduction band current, you have the free electrons. They are wandering around in your material. If you apply an electric field, so electric field from here to here, this electric field will cause the electrons to start moving in the opposite direction, to drift in the opposite direction. So this is current, this conduction band current is due to electrons that are in the conduction band. They have enough energy to be free electrons. And they move opposite to the applied electric field. So they are simply all moving in the applied to the electric field, and then they cause current, of course, in the opposite direction as we agreed. Current is by definition the motion of positive charges, and it's opposite to the motion of negative charges. Another type of current that we'll be talking about, which is a slower type of current. Slower. Why? Because an electron will be jumping from one valence bond to fill a hole in another valence bond, and then to fill a hole in another valence bond, and then to fill a hole in another valence bond, and so on. So you can see it does not move exactly in the direction of the applied field. So this is equivalent to electrons moving opposite to the field, or to holes moving in the direction of the field. And this is how we usually think of it. We think of it as equivalent to motion of holes in the valence band. So this is called valence band current. Okay, so there are two types of current. One of them is way faster. Here the mobility, and I spoke to you about the mobility earlier. The mobility here will be way higher because electrons drift opposite to the electric field directly. While here the electrons will keep on jumping from one valence bond to fill a hole in another valence bond, to fill a hole in another valence bond, and so on. So it does not really move exactly in the direction opposite the electric field. And this motion of the electrons is equivalent to holes moving in the opposite direction. And this is why we consider this valence band current as motion of holes, as I said, in the valence band in the direction of the applied electric field. So just remember this. We have faster conduction band current where the drift velocity is bigger. We have slower valence band current where the mobility is slower. Semiconductors by themselves, they have very little conductivity. And we can improve this conductivity by adding impurities. Adding impurities is a process called doping. And I will be sharing with you a video about the process of doping, how it happens and so on. But somehow they introduce some impurity atoms in the middle of the semiconductor material. Like here we have antimony atom that was introduced in the middle of the silicon. And we introduce them with certain concentration. Maybe they are introduced as gases, hot gases, or as ions, or whatever the case may be, but we introduce them into the material. And the antimony here, this antimony, it has 5 electrons in the outermost shell. So it creates a covalent bond with 4 neighboring silicon atoms. So this is one covalent bond, the second one, a third one, the fourth one. And then, because it has 5 electrons of its own, there is a 5th one is really available for conduction. So every antimony atom will contribute 1 free electron, and this raises the conductivity significantly of this material. So this material is called an N-type material. Why we call it an N-type material? Because every impurity atom will contribute 1 free electron. Then the concentration of the free electrons is way higher than the concentration of say free holes. While we have here something different, if we introduce a material like boron, here this boron, and boron has only 3 electrons in its outermost shell. What boron does is that it creates a covalent bond with 3 of the silicon atoms, and there is a hole left in the 4th covalent bond. There is no electron to fill it, and this hole is ready to be filled by another electron. So this material in every boron atom, every boron atom will contribute 1 hole, and as we agreed earlier, this hole is equivalent to a positive charge. So we call this this material which is rich in holes, we call it a B-type material. And you'll see that the interaction between N-type materials and B-type materials is what really create different types of semiconductor devices, like diodes, like transistors, and so on. So, as we agreed, if you want to create an N-type material, you have to include an impurity. But this impurity has to be a pentavalent impurity. Pentavalent meaning that it has 5 electrons in the outermost shell, like antimony, the one we discussed earlier, like bismuth, like phosphorus, like arsenic. All these have 5 valence electrons in the outermost shell. They share 4 with the neighboring semiconductor atoms, and each one of them will contribute 1 free electron. We call these impurity materials donor atoms because they donate. Each one of them will donate 1 free electron. At room temperature, the thermal energy is sufficient to make these electrons break from their atoms and then become free electrons. And in that case, in that N-type material, we say that the majority of carriers are electrons, and the minority carriers are holes. And this, as I said, this is called the N-type material. For this type of material, if you apply an electric field to this type of material, these free electrons will start to drift opposite to the electric field, and they drift in a fast way opposite electric field, creating conduction band current. Now there is a formula that is not in the book, but it's very one to remember, that the concentration of, this is coming from quantum physics, concentration of electrons multiplied the concentration of holes is equal to the intrinsic carrier's concentration squared. This number here is 10 to the power 20, and this number we're going to be using in a later example, as I will show you. But just remember, as you have more electrons, you are bound to have less holes, because the product is equal to this number squared, and this one is a fixed number. Okay, so in N-type materials, we introduced a wealth of electrons. This means that the hole concentration will have to be way smaller. And this is coming from quantum physics. Np is equal to Ni squared. This is electron per centimeter cubed. This is hole per centimeter cubed, and this is here per centimeter cubed. And as I explained earlier, if you want to create a p-type material, you have to introduce a trivalent impurity, an impurity that has only 3 valence electrons in the outermost shell. Some of these are boron, indium, and gallium. It will create 3 covalent bonds with neighboring electrons, but will be 1 hole left to be filled by an electron from somewhere else. And we call these atoms acceptor atoms. Why they are called acceptor atoms? Because they are willing to accept 1 more electron. At thermal energy, you can see we have these holes created, and they are ready to be filled by other electrons, and they represent effectively positive charges. In this case, the majority of the carriers are holes, are positive charges, and the minority are electrons. And we call this type of material p-type material. The motion of holes, as I explained to you earlier, is slower than the motion of electrons, because you have to move from one covalent bond to another covalent bond. It does not really move directly in the direction of the electric field. So this is what give rise to the valence band current, which is a little bit slower type of current than the conduction band current. Okay, I will show you now an example. We have now silicon, and silicon was doped with phosphorus at concentration of 10 to the power 17 atoms per centimeter cube. This is the concentration of the impurity that we introduced. And remember, phosphorus is a pentavalent impurity, so it has 5 electrons in its outermost shell. I would like you to find the majority and the minority carrier concentrations in this case. What is the majority carrier concentration? What is the minority carrier concentration? Because we introduced phosphorus, and phosphorus has 5 electrons in the outermost shell, every phosphorus atom will contribute 1 electron. And this electron becomes free at room temperature, so we really have this number of free electrons. And this one exceeds a lot the intrinsic electron concentration. So effectively, this is the number of electrons we have. And by intrinsic, I means the electrons available from the silicon atoms themselves. There aren't really many electrons available. This number way exceeds the intrinsic carrier concentration, and this is why the concentration of free electrons, which is the majority carrier, will be 10 to the power 17. How do we get the minority carrier concentration? Well, we use the relationship NB equal to Ni squared, and this will give us the concentration of the holes that we have in this case. So here, as I explained, phosphorus has 5 electrons, 5 valence electrons, then it is a donor, then this means we have N-type material, and the carrier concentration, assuming that the phosphorus atoms have all been ionized. So each one of them has already donated the 5th electron, and this 5th electron is already free. Then we have 10 to the power 17 electrons per centimeter cube. This is a concentration of the electrons. Centimeter cube there minus 3, but 10 to the power to the exponent of minus 3. It's 10 to the power 17 electron per centimeter cubed. The intrinsic carrier concentration is 10 to the power 10. So it's 10 to the power 10. This is Ni. So if you have a piece of silicon with no doping, you have number of electrons equal 10 to the power 10 per centimeter cubed. You will have number of holes equal 10 to the power 10 per centimeter cubed. But this number is way higher than this number. Then this number can be ignored, and this becomes the electron concentration. If you want to get the whole concentration, you divide Ni squared, which is this term. Ni is 10 to the power 10 per centimeter cubed. It's called the intrinsic carrier concentration. You divide Ni squared by n. So this is Ni squared, it's a constant. You divide by 10 to the power 17. You get that the concentration of holes is very little. It's only 1,000 holes per centimeter cubed. So this is indeed an N-type material, and the dominant or majority carriers here in this case are electrons.